This lesson, we are going to apply all of the properties that we practiced in our last lesson for logarithms, and we also reviewed the exponential properties, but we're going to combine that with our previous lesson about how to rewrite logarithms and exponential equations in other forms, and then we will solve these. So there's no new rules in this lesson. There are different approaches to take, and many times you can use different approaches on the exact same problem. So sometimes students just find an approach they like best and use that one the most. The only hesitation to that is the last one, which is solve graphically, because when it says those are really geared best for the answers that want decimals. And so we will do that at the end, and we'll show you how to do it on the calculator. But if they need an exact answer, that might not be the way to go about it. Other than that, you can choose the one you like, but sometimes not all choices work. So what we have on our next few slides, and you can see this isn't an extremely long PowerPoint here, is I've got like a couple of examples for each one of these. So this will be the next slide, and then the one after that, and so on. Okay, and that's going to take care of what we're doing because there's no new information here. It's just how to apply it. These are all the tips, and here's how we go. This is our first tip: write expressions in terms of the same base. The rule that we're actually applying here as far as exponents go is if a to the x equals a to the y, then x has to equal y. So we look at the base that we have, and you think, okay, the base over here is 2, so how can I rewrite 8 as 2 to the? So I have 2 to the 2x is equal to 2 to the, well, 2 times 2 is 4, times another 2 is 8. So 8 is 2 to the third. So now I have the same base, and that's where this rule applies. If the bases are the same, then that means those exponents have to equal each other since this was an equation. So now I can just drop off those bases and say 2x has to equal 3. So x is equal to 3 over 2. Well, that wasn't hard. Okay, now over here, the base of this exponent is 3. So if I'm going to rewrite them in terms of the same base, I can't change this one. So it's this one I have to change. And what I know is that 27 is 3 times 3, which is 9, times another 3. If this is 1 over 3 to the third, then 1/27 could just be written as 3 to the negative 3, because remember what we said about a negative exponent just means it's on the wrong side of the fraction bar. It's just a notation. So 3 to the x squared plus 4x is equal to 3 to the negative 3. Now that I have the same base, I know those exponents must be equal. So x squared plus 4x has to equal negative 3. Once you get to this, I mean, our good old-fashioned approach is to say solve by any appropriate method. But what you're going to find is very often you're going to be left with a quadratic. And so we're going to get it equal to 0. I'm just bringing that 3 over. And then you can solve this by the quadratic formula if that's your go-to. You know, I like to factor every single time it will factor. And what multiplies to 3 and adds to 4? Oh, well, that's 3 and 1. So we get x plus 3, x plus 1. And my solutions then are negative 3 and negative 1. A word of warning, actually. Every single time you get a negative, I want you to really slow down. It is quite possible to have negative answers, but what it's not possible to do is have a negative base of a logarithm or a negative argument in a logarithm. So in this case, since I go back and I look at my original, this was up in the exponent, and you can plug it in, but this one checks. But you just want to make sure you look at that, and we will have a couple where not both the answers we give will work. All right, so if we're not going to rewrite it in terms of the same base, we could take a logarithm of both sides of the equation. You know, in algebra, if you do something on one side of the equation, you can do it to the other. And so this is actually easier than it seems. You just write the word log in front of both parts. Then we can apply the fact that this exponent on a logarithm argument moves to the front. So now I have x log 15 equals log 30. Now you don't have to take a log base 10. It's the one I tend to go to, but some people like to write ln in front of both sides or something. I just tend to do plain log. But now if you want to get x by itself, that's multiplied to log of 15. You just divide both sides of this equation by log of 15. So x is equal to log of 30 divided by log of 15. Now from here, this is an exact answer, but we could get a decimal approximation on the calculator. So alpha y equals enter, and I can do log of 30. Now it's going to automatically open parentheses. You should close them. And then I put it over log of 15 and close my parentheses again. And I get 1 point. And typically, I mean, always round to whatever your instructions say. But logarithms, by habit, on almost everything, go to 4 decimal places. So that's this 5 is going to make that 59 bump to a 60. So it'll be 25.60. 2560 if we took it to 4 decimal places. On this next problem, I could immediately take a log of both sides. However, then I would have all of this stuff inside a single logarithm, and I would have to break this one up into 2 logarithms. And your better approach is, first of all, just isolate the exponential part. So what I'm going to do first is simply divide both sides of this by 1,000. And I don't know what that extra 0 was for. Please just let me scribble that out. So here the 1,000 cancels with 1,000. I have e to the 0.09t is equal to 5. I can take a log of both sides, and I can take just like I did on this first one, log, just regular log. However, since it's in base e, I am choosing to take an ln of both sides. The reason I want to take an ln of both sides is, if you remember, this one is in base e, and so those bases are the same. And if the bases are the same, then essentially this entire left-hand side just equals that 0.09t. So 0.09t equals ln of 5. And then to get t isolated, I can divide both sides by 0.09. So t is equal to, we'll pull up that calculator. Again, that's the exact answer, but we're going to have an approximation. So alpha y equals enter. I want you to be able to see it while I put it in. So this is what I'm putting in. ln of 5, open parentheses, so I'm going to close them, over 0.09. Some of you might be wondering, why does she always put the 0 in front? I could just put 0.09, but I find that people like it to look the same. All right, so this one is equal to 17.8826. And this one is actually not at the equal. This is the approximation. This one is exactly what it equaled up here. So again, read your instructions. Do they want an exact answer, or do they want a decimal approximation, and how far they want you to round it to? So here we took a logarithm of both sides. When you have a base e, it's handy to make that logarithm be base e also, so use an ln. Now, if you have more than one logarithm, you're really going to need to combine those. You're going to want to combine them. It's going to make the world better. So write this as a single logarithm. Well, what happens when we write with a single logarithm, as you'll remember from the last section, if it was plus, it becomes multiply. So I will end up with log of x times x minus 9. And that has to equal 1. Now, as I've written it, it's in base 10. So if I rewrite this in the other form, then this is 10 to the 1 equals all of that. So 10 to the 1 is 10. So that equals x times x minus 9, which of course is x squared minus 9x. Now if I write that this equals 0, that means I've got to subtract 10 to the other side. This one does factor. So I get x minus 10 and x plus 1, which means I have solutions of 10 and negative 1. Now, the 10 is not scary to me, but as soon as I see this negative, I want to look at my original. A negative 1 does not work right here. You cannot have a negative as the argument. It also doesn't work over here. It doesn't matter if your solution is negative. It just matters what it ends up being as a value. So in this case, what we have is that we found an extraneous solution. It means we did all the work right, but it doesn't check. And 10 is the only actual solution. Okay, on this one, now let me say first of all, you've got 3 logarithms. You can combine them all. You can combine 2 of them, and you can get the right answer with lots of approaches. So I could take that over and make this one be log of this is equal to log of x plus, log of the other one. It doesn't matter. You can, like I said, there's a lot of approaches that work as long as you're just applying the rules. But if I just combine those 2, then I'll end up with log base 2 of x plus 20 over x plus 2 is equal to log base 2 of x. And remember on that earlier slide where we took a logarithm of both sides? But guess what? We can also unlog both sides. So I have x plus 20 over x plus 2 is equal to x. Now you can't solve for a variable until you get it out of a denominator. So the very next thing I need to do is multiply so that I don't have that variable in the denominator. So if I multiply both sides of this equation by the x plus 2, then over here on the left, I get it out of the denominator. So then I'm left with x plus 20 is equal to x times x plus 2. Let's go ahead and distribute that. So that's going to give me x squared plus 2x. Once again, I've got a quadratic. So I'm going to take, I like to leave my x squared term positive, so in factor, I'm going to take those other ones over to the other side. So I have x squared. Now 2x minus x is just 1x. And then that 20, I had to take it over by subtraction. What multiplies to 20, or to the negative 20, but subtracts to 1? Well, that's going to be x plus 5 and x minus 4. So my solutions for this, for that very first one, I would get a negative 5. And for the second parentheses, I get a positive 4. Now again, this negative I'm really concerned about, so I want to go up there and check. Negative 5 plus 20 is positive 15, so it's fine in that one. But when I move over here, negative 5 plus 2 is negative 3. It doesn't work in that one, and it certainly doesn't work in this one because that would just be log base 2 of negative 5. So that one, you can't have a logarithm with an argument that's negative. So my only final answer, negative 5 was extraneous, and 4 is the final answer. So we've looked at several approaches. Now let's do a rewrite approach. Now this problem should look familiar. A couple of slides back we did this problem, but we didn't do it the way I'm about to do it right now. So we're going to use a different approach to it. And on this one, we're just going to rewrite. And for a rewrite, you start at the base. And this is exponential, so I'm going to turn it into logarithmic. I'll start at the base, which the log base will be 15. Go to the other side. So log base 15 of 30 is equal to x. Look at this, guys. This is already ready for your calculator. That's the exact answer, You want a calculator answer? Don't forget, you can go to math. You got to scroll a long way. Log base. Now, the log base then is 15 and it's of 30. And we get our answer. This is the exact same answer we got earlier when I put it like a fraction, and I put log of 30 over log of 15. So in the other one, the very first thing we did was take a log of both sides, and here we're doing a rewrite, but they get the exact same answer. So it doesn't matter which way you do it. This is the one that is 1.2560. And that's the approximate answer. Now this one is in a logarithm, so we're going to rewrite it as exponential. So again, you focus, oh, the base is 5. So the base of our exponent will be 5. Start at the base, go to the other side, so 5 to the 4th is equal to x. Boy, that's pretty direct, isn't it? We're not going to have to approximate this. We just need to say 5 to the 4th. And it's 625. So the only method we haven't looked at yet is actually the calculator method for graphing. There are 2 ways that we can actually do this on a calculator for graphing. What you can see here is one of the methods. We can solve graphically by intersection, and this is typically the one I like because you don't have to move anything around. What you do is you go into your y equals, and I know these are awfully small. I'll bring it up and show you how to do it. But you go into your y equals, and you put y1 is equal to the left-hand side of your equation here. And then y2 is equal to the right-hand side. You graph them. Now, when we graph these, if you don't see the intersection of the 2 sides, you will need to change your window. Now, this one I didn't need to change my window on, but that is something to watch for. So this one may require that you change the window so that you can see the intersection. If you can see the intersection, then you can tell your calculator to calculate that intersection, and you give it a left bound and a right bound, or you give it the first equation and the second equation, the first curve, second curve, depending on your calculator model. I thought they all said curves, but recently somebody told me that the phone app is different. So let me bring this up, and this will just be so that it's big enough for you to look at, okay? Just trying to make that bigger so that you can see it. I'm going to go to y equals. First of all, I have this plot on. You probably don't unless you're also in stats class. So I'm just going to turn that off because that can mess up your graph. Also, how strange are these dots? I don't know why they're there. I'm going to adjust that when I get there. They should all just be lines, but I'll show you how to adjust that if you didn't know. So y1 is equal to the left-hand side of this, which is x times e to the 3x minus 1. So x, and then we have second ln gives me e to the 3x minus 1. Now on this next one, it's probably no big deal, but I'm going to back up, and I'm just going to hit enter a few times. I don't care about the color. The color's not important at all, but here you can see that I can change different options there by going over. So I'm going to hit OK now. So I've just changed that. I know it doesn't look as wide as that one. Who cares? And I'm going to say it's equal to the right-hand side of my equation, which was 3. All right, now we're going to graph them. And notice this window doesn't look like that window. That's what I'm saying, that you might need to change your window. So to change your window, there's several ways you can do it. If you want to go negative 10 to 10, I can just hit zoom 6. And that's your normal negative 10 to 10 viewing window. Okay, otherwise you can hit window and tell it where to start and stop on your minimums and maximums. But here I can see my intersection. So I want it to calculate it. So I hit second trace. Just above trace it says calculate. Go down to option 5 here, which is intersect. You don't have to hit this arrow key over and over and over. When I do that, you can watch this go down, but if I know it's a 5, I can just click 5. Now notice mine asks for first curve. Yours might ask for a left bound. But I'm just going to click enter, 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 really, because this is my first curve, so enter. That's my second equation, enter. I'm not going to waste the time on my guess, so I hit enter again. And here's the intersection, right here. And this x value of your intersection corresponds to the x value that was the solution to the equation, okay? Because we were just solving for x. There wasn't a y in this. So I don't need the y of the intersection. And it's the 0.620939. So that's really small down here, but that is the same answer. So that's one method of solving graphically. The other one is very similar, but instead of using the left-hand part of the equation and the right-hand part of the equation, you set the entire equation equal to 0. So looking at this equation right here, if I set that equal to 0, I'd have to subtract 3 from both sides. And so I would end up with x times e to the 3x minus 4, x second ln, e to the 3x, and then we get minus 4. So see, I'm putting it all on that one line then. Now, I know I put it in y2. I should have just put that in y1 probably, but it really doesn't matter. You just want to put it in one of your equations. So I'm going to hit graph, and what you see is the graph of the one equation I have in there. But since your equation is set to 0, you're wanting to know where it equals 0. So if you do it this way, you want to tell your calculator to calculate not the intersection, but the zeros. And on this one, it gives me a left bound. Then I use my right arrow key over to get somewhere to the right of it. Again, doesn't matter if you're above or below, just to the left and to the right. And then I skip the guess, and I get the exact same answer. So on one of them, you just use the left hand and the right hand, and you graph two equations, find the intersection. On the other approach, you get it all over to equal 0, and then calculate the 0. Again, the one difficulty here is that we're likely to get decimals, and sometimes your homework may want an exact answer. That does finish up this lesson, and we are getting really close to done. Don't forget to ask the instructor if you need some more help.